Standard error. Standard error is one type of data analysis that we'll do in this class. So why do we even need to do data analysis? We have to watch out for the manipulation of data because surely by now you've graphed things in several different ways, but you may have noticed that sometimes graphs can be a little bit different. So people are able to manipulate data, and advertisers like to do this all the time in order to kind of suck you in and get you to buy their product. So let's say we have this brand new weight loss drug, and it's called the Liberator. Participants in our study who took Liberator lost 4 times more weight. Well, that sounds amazing, doesn't it? So we've got 2 groups. One group is given a placebo. They're given a drug that is not the actual medication. It's just something that they don't know is not the actual medication. And group B gets the actual Liberator weight loss drug. Well, then, if group A had an average weight loss of 1/4 pound, then group B can lose 4 times more weight, and all they lose is 1 pound. So advertisers are manipulating the data. What they're saying is technically true, but they're making you believe something that the drug is better than what it actually is. So COVID-19, this was a graph that was out not too long ago and makes it look like the male patients are much more likely to contract COVID than females. But take a look at the scale. It's only going up by 2 people each time. Whenever you change the scale to make it a little bit more reasonable, you notice that maybe there is a slight difference in the male and female population, but it's not the same. It's not as big of a difference as this graph is making it out to be. So they're manipulating the data. So why do we even want to bother with data analysis? This allows you to have a measure of confidence that gives us better precision. You can make a claim with confidence. You can decide whether the results that you have come up with on your experiment are just due to chance or if there is a significant difference. Is there actually an effect of that independent variable on your experiment? Standard deviation is helpful to understand. We won't actually do standard deviation, but like I said, it's kind of helpful to understand. So the mean score, the average score, is the line in the middle. When we look at data, we take this range of values to be pretty much all the same. So all of this we consider to be the same. Then this range of data, probably less. This range of data, definitely less. So same thing on the other side. This range of data, probably more. This range of data, definitely more. This is a bell curve, and chances are you've seen a bell curve before. And within this bell curve, our data we expect to fall within 95% of the mean. So if this is the mean right here, we expect the data to fall somewhere in these 4 sections. That's 95% of the mean. This is the mean, so this is 1 standard deviation. This is 2 standard deviations. Same thing, mean, 1 standard deviation, 2 standard deviations. So we know that 2 standard deviations of the mean, we have a 95% confidence that that's where our data is going to fall. Standard deviation is basically how spread out the data is. So in the first graph, we have a standard deviation of, let's just say 5, standard deviation of 5. It shows that all of our values are clustered tightly around the mean. The second graph, let's say, had a standard deviation of 10. The values are more spread out from the mean. So here is looking at standard deviation just like that, but it's a little bit more realistic. It has, let's say, more data on here. So graph A, graph B. At first, it looks like this second graph has more data, but whenever you're looking at graphs in AP Biology, you have to pay attention to the labeling. Look at the y-axis. This is 2, 4, 6, 8. This hard to see, I know, but it's 0, 5, 10, 15, so the count is different. So that's one way you can manipulate data, is by changing the counting pattern on the y-axis. So it looks like there's more data here, but there's not. It's just they're choosing to display it differently. So let's say this is our standard deviation of 5, and this is our standard deviation of 10. The data is more spread out with a larger standard deviation. In these two graphs, once again, we look at the count, 5, 10, 15, 20, 0.2, 0.4. So once again, the count is different. The graph curves look the same, but on this side, we have much more data because the count is higher and we have more data bars. The count is lower and we have much fewer data bars here. More data means that we have more reliable results. We can have more confidence. So standard deviation is great, but we really don't use standard deviation in our analysis. We are actually using standard error. Standard error is the accuracy of an estimate or the accuracy of a mean. So mean is an average. This is looking at the accuracy of that average. It gives us an idea of whether or not we have sampling error. The higher the number, the more spread the data, and the less precise the mean. A small standard error means that it's more precise. Standard error tells us how far your sample mean deviates from the actual population, what the actual sample size is. You want to have as large of a sample size as possible. So we're looking at prices of different types of fruit here. Using standard error to give an analysis of individual items, we can take a look at different prices of fruit to determine the amount of deviation of the price of apples, which is really not too bad. Plums are not too bad. But oranges have a high standard deviation here. There's this high standard of error bar. You could use that to infer what's the next price you'll have to pay for that particular fruit. So if this represents the average of the price of apples in different states, 12 major cities, this shows how confident you can be that the next apple that you get from another major city, that the price is going to be within this range. For oranges, the average was higher, but we have a bigger standard deviation here. So we don't have as much accuracy, so you can't be quite as certain that you're going to get this price. You can only be certain that the next orange that you buy is going to be somewhere within this range. Although plums have a small standard error bar, whoops, where's my cursor? There it is. Although plums have a small standard error bar, it's still a big difference, especially depending on the mean here. So their mean, the average price of a plum is 50 cents. But this is saying that you could be paying anywhere from 25 cents to $1 per plum. That's a pretty big difference. So when you're finding standard error, when you're analyzing using standard error, the bar itself, the bar that you draw is the mean. It's the average of your data. So you're going to add everything up and divide by the number of data points that you have. So for example, the mean was 5 kilograms. We always do plus or minus 2 standard error of the mean. So whenever you calculate your standard error, you add that to the mean or subtract it from the mean. Because it's plus 2 standard error of the mean, I take my standard error and I add it twice. So 5 plus 1.25 plus 1.25 gives me a plus 2 SE of 7.5. Then I subtract it from 5 twice. So 5 minus 1.25, and that minus 1.25 gives me 2.5. That tells you where your standard error bars should begin and end. So this might end up being make a little bit more sense for us because we're going to be applying standard error to experiments and experimental data. So in this experiment right here, we have a control group, and then we have a group that's treated with a chemical, and we're looking to see what is the enzyme activity, and is the treated group, is that treatment actually having an effect? So the bar represents the average. The I-beam, this is the standard error of the mean, and we do plus or minus 2 standard error of the mean. Then we take a look and compare those standard error bars. If they do not overlap each other, or the overlap is not very significant, that means that most likely the treatment made a difference. So these beams do not, the standard error bars, they don't overlap. That tells me that most likely this treatment, my independent variable, did have an effect on the experiment. If there is overlap, especially a lot of overlap, then that tells us that there is no statistically significant difference in the treatment. So even though here the mean is different than this mean, so this average is lower than this one, so that looks like this treated group actually had an effect, but because the standard error bars overlap, that's saying that the difference in the mean is not statistically significant. So that's like saying if I flip a coin 50 times, if I flip a coin 100 times, I expect it to land on heads 50 times and land on tails 50 times. But I flip the coin and it ends up being 49 heads and 51 tails. Is that the same as 50-50, or is that actually a significant difference? When we analyze that, we'll find out that 49-51 is actually not a significant difference, and it's basically the same as 50-50. So that's what this is saying right here. After we analyze the data, the overlap in these bars is telling us that the difference in the averages is not statistically significant. The more overlap, the less statistically significant that difference in the data is. So this is on the worksheet. Let's go ahead and flip back to that. So you've got this information. And let's say for a moment that we are comparing different brands of fertilizer. So I'm going to edit this just a little bit. And so here I have 2 brands of fertilizer, brand A and brand B, and I want to see which fertilizer is better for my plants. Well, if I run the experiment, collect the data, and analyze the data, checking on the height of plants, it looks like fertilizer brand A makes my plants grow taller than fertilizer brand B. But if I use my standard error to analyze, I have an overlap in those standard error bars. So that tells me that really, statistically speaking, even though this one's growing a couple centimeters more than these plants, statistically speaking, there really is no significance in that difference. The less the overlap, then the difference is probably not statistically significant, but it's still overlapping. If I've got no overlap whatsoever, then it may be that that fertilizer is having an effect on those plants. So, even though fertilizer brand A averaged taller plants, the difference is not statistically significant because of that overlap in the standard error bars. Where I have no overlap, fertilizer brand A most likely had an effect, but we're never 100% confident. So we always want to have more analysis. Standard error is derived from standard deviation. We don't do standard deviation, we just do standard error. And we have a simple formula for that, and we can actually use Excel program on the computers as well. But to kind of give you a visual, so remember we said that this looks like there's a whole lot more data points, but we had to go back to the count to see that that's not necessarily the case. Probably have the same amount of data. So for A, we have standard deviation where most of the information, most of that data is crowded around the mean, crowded around the average. It's kind of hard to see on this, but that's 50 kilograms, and the mean, the average on this one is also 50 kilograms. So for both graph A and B, the bar represents the average, which would be 50 kilograms. It's the same for both. But my standard of error for A is going to be much less than my standard of error for B, because my data is very close to the mean, so all of my data points are relatively similar. These data points are very spread out, and so I don't have as much confidence. I need to spread out my standard error bars in order to say the next time I pick up a random sample of individuals and find its mass, then it's going to be within this range right here. For this graph, the population is much more similar, so I'm fairly confident that I can get that next mass, and it's going to be somewhere within this range right here. Now these graphs do represent differences in the amount of data. So the bell curve is the same on both. The average is still the same on both. But this time, because I have more data, my standard error probably isn't going to be as small as it is on A, so it's going to be a little bit bigger. But I have more data, so I always have more confidence, more reliability with more data. Less data means my standard error is probably going to be a bigger standard error because there's less data and it's relatively spread out as well. And just so you understand that standard error can also be graphed using points in a line graph. So this would represent my average, and this would represent the standard error. Average, standard error. So how can we use Excel to help us find standard error? And use it to help us graph standard error. All right, so I've got two sets of data from an experiment. The first thing that I need to do is I need to find the mean because the bar represents the mean or the average. So for this set of data underneath in one of the boxes, I'm going to type average. Oh, I'm sorry. I'm going to type equals average. There we go. And then in parentheses, I'm going to put the item numbers that I want to average. So this is column A. I'm going to start at A3, and I want to average everything from A3 to A17. So I'm going to type in A3 to A17, and I'm going to close those parentheses. And then when I hit return, it gives me an average. So same thing for this one, equals average. But this time, the data is in column B. So I'm going to average everything from B3 to B17. B3, B17, and it gives me an average. So next, we have to find, or make the Excel program find standard deviation because standard deviation is related, or standard error is related to standard deviation. So this formula is equal STDEV, open parentheses, what do I want to, which number range am I finding standard deviation for? So that is A3 to A17. And notice how it's highlighting it so I know for sure that I've got what I want. Close parentheses, equals. I'm going to do the same thing for this one. Standard deviation, B3 to B17. Okay. Now I tell it to find standard error for me. Okay, the formula for standard error equals, and then you have to put in the box that has your standard deviation. So I'm putting in A20 because that is the square that has standard deviation in it. Slash SQRT, open parentheses, count, open parentheses, where am I counting from? From A3, oopsies, A3 to A17, close parentheses, close parentheses. And there's my standard error, 2.21, because I'm going to round that up. So in order to put plus or minus 2 standard error of the mean, I would do 4.42, add it to my 26, or 4.42, subtract it from my 26 to find the top and the bottom of my standard error bars. And so just to show you again, so I'm doing B20. That's where my standard deviation information is. Slash SQRT, open parentheses, count, open parentheses, B3, B17, close parentheses. And so you can see I have a almost half, not quite half, standard error on this one than I have on that one. So 1.26. So 2.52 would be my plus 2 minus 2 standard error of the mean. So I would add 2.52 and subtract 2.52 in order to get the top and bottom of those error bars.